Hello, geometry data people. So we're still in Unit 5. We are now moving on to Investigation 3. So today we're going to cover Lessons 1 and 2 in Investigation 3, and it starts on page 89. So on page 89, at the top of the page, they're talking about the shortest distance theorem and the fact that if you draw a line from a point tangent to a circle, that tangent line is going to be perpendicular to the radius where they touch at the tangent point. And it connects to this other theorem called the shortest distance theorem, which basically says if you have a point, like this point C, the shortest distance to go from point C down to this line AB is going to be a straight distance to D at a right angle. Any other connection that you make from point C to that line is going to be a farther distance than from C to D. And you can see that if we connected, say, to point A over here, you can see that that distance is longer than CD because that's the hypotenuse of a triangle, and that's always the longest side, right? What if we connected to point B over here? Again, that's the hypotenuse of a right triangle, and the hypotenuse is always the longest side. So the shortest distance is going to be the one that goes straight at a right angle. And how that's connected with circles is on the back of this page, on page 90. I'm just going to use one of these circle diagrams as a way to demonstrate. All right, so we have here a circle. So here's a circle, and the center point is A. All right, and here's our circle. And we have this line over here. We have this line that goes along the side here, and it's tangent. It only touches at that one spot, okay? And where it touches, that is going to be a right angle, a 90-degree angle. And again, you can see that if we started at this point A and we connected to any other point on that line besides this point right here, it's going to be farther away because remember the definition of a circle. All the points on the circle are the same distance r away from the center, right? They're all one radius away. So for example, over here, that point right there is one radius away. That's the same distance, and that does not get us to the line. The line is farther away than that. If we came over here, that point is one radius away. To get to the line, you would have to go farther than a radius. So this is the closest distance, is one radius, and it's right there at the tangent point, which is at a right angle. Okay? So we're going to use some thoughts like this as we progress through the lesson today. Okay, so we're going on to page 91, and we're just going to solve some problems. So these next couple problems are not too complicated, and it's kind of interesting how it works out. So we have a diagram here. I wrote the numbers bigger because they're kind of hard to read. That's point A. So we have a circle, and the center of the circle is point A. And we have this other point F that's out away from the circle. And we have a line that comes from point F, and it just touches the circle at point D. And then we have another line through F that comes up here and just touches the circle up here at point C. And they tell us that this angle here, out here at point F, where those two lines cross, they tell us that that's a 55-degree angle. What they want to know is how big is angle CAD? What is the measure of this central angle here inside the circle? Well, guys, look at what we just drew. With these tangent lines and the radiuses, the radii, that go from the center out to the point of tangency, the point where the line is tangent, and then back to that point F out there in space, we just drew a quadrilateral. And if you remember from when we talked about polygons and triangles. A quadrilateral, the interior angles, there's 4 angles inside that quadrilateral, and the 4 interior angles add up to 360 degrees. They sum to 360. Well, we already know this angle's 55 degrees. What's this angle? What did we just say? When there's a line that's tangent, where it intersects with the radius, it's going to be a right angle. It's going to be a 90-degree angle. Same thing on this side. The line that is tangent, it intersects the radius. That is also a 90-degree angle. So the only one that we're missing is this central angle, but these 4 have to add up to 360. So our missing angle plus 90 plus 90 plus 55 have to add up to 360. 90 and 90 and 55 is 235. So this is x plus 235 equals 360. Remember algebra, subtract, subtract. We'll subtract 235 to cancel because now that's 0. And we get x equals, we subtract 235 on the other side also. 360 minus 235 is 125 degrees. And that is our angle, okay? So this is called the point of tangency. Okay, just so you remember that. And that's the point of tangency. That's where the line is tangent to the circle. All right, let's do one more. So here again, circle, center A, point F. Here's our points of tangency at C and D. This time, they gave us the central angle. They said this angle is 137 degrees. They want to know this angle. That's the angle we don't know. So again, where the radius meets the tangent at the point of tangency is a 90-degree angle. Where this radius meets the tangent at the point of tangency, that is a 90-degree angle. We have 90 and 90 and 137 and x. Right? And what do they have to add up to? They have to add up to 360 degrees because this is a quadrilateral. This is a 4-sided figure, 4-sided polygon. And a 4-sided polygon always has interior angles that sum to 360. So if you add those guys all up, 90 and 90 is 180, 280, 317 plus x equals 360, right? Minus 317 on both sides of the equation, and x equals 43 degrees. So this angle out here is 43 degrees, okay? So let's take this idea and go one more step beyond that. So here's one more problem on the back of this page. Okay, so this would be on page 92. And we have our circle with our center A, and we have a point E away from the circle so that we have lines which are tangent at points C and D with radius that goes from A to C at a right angle, A to D at a right angle. Okay, now let's see what else they tell us. The measure of angle CED is 60, CED. So this is a 60-degree angle. However, what they're asking us is if they tell us the circumference of the whole circle, they want to know what is the length of this minor arc. So this is what we did in the last lessons. So the first thing we need to know in order to calculate a minor arc, remember the first thing you need to know that central angle. So we have to figure out what that central angle is. Okay, so just like we did on the other two problems, here's our quadrilateral. And we know the angles add up to 360. So here's a 60 and a 90 and a 90. Has to equal 360 when we add them to our missing angle x, right? So right here, 60 and 90 adds up to 240. So whatever our angle here, whatever our central angle is, plus 240 is going to equal 360. So if we subtract, we get that our central angle x is 120 degrees. Good, we needed to know that because now you're probably remembering that in the last lessons, to find that arc length, what you did is you compared your angle measurement compared to 360. So the angle compared to all the way around in a circle times the whole circumference gives you the part of the circle, right? Gives you the arc length. Well, now we know that the angle is 120 divided by 360. So that's what part we want of the whole circle. And they told us the whole circumference was 96. They didn't give us units, so we don't know if it's inches or miles or feet or what. 96. So 120 divided by 360 is the part we want of the 96 times the 96. And if you do that, you get an answer of 32 is your arc length. Okay, and that is our answer. All right. So we used our points of tangency to figure out the central angle measurement, and then we use that to figure out the arc length. All right, so now we're going to go on to lesson 2 for a few minutes, and on page 97, we're going to talk about another triangle theorem, and it's called the hypotenuse leg congruence theorem, and basically it says if you have two right triangles and their hypotenuses are congruent, same length, and one pair of their legs are congruent, then the triangles are congruent. And once the triangles are congruent, that means all of their parts are congruent, right? So here's what we have here. We have, again, a circle with a center, right? And we have a point off the circle, and we have a line that's tangent at point E, and that means there would be a radius. And we have another line from that point that's tangent out here to point D, and that would have a radius. And we know that these are right angles because the radius always meets the tangent line at the point of tangency. It's always a 90-degree angle. Same on this side, right? And what they want us to prove, they want us to prove that this length out here, DC, is the same length as this side here, AC. So I'm going to draw you one quick thing that's going to make all of this super easy. I'm going to draw a line from A out to C, a line segment. Okay, so what if I do this? Okay, now look at what we just got here. We now have two right triangles. Okay, so we have triangle AEC using that line I drew. Okay, and we also have right triangle ACD using the same line that I just drew, the same line segment. Okay, now let's think about that hypotenuse leg congruence theorem. Well, are the hypotenuses. This is the hypotenuse of the pink triangle. It's across from the right angle. This same segment is also the hypotenuse of the blue triangle because it's opposite from the right angle, right? So these two triangles, their hypotenuses have to be congruent because it's the same line segment, right? So are the hypotenuses congruent? Check, okay? We need one pair of legs that are congruent. Well, this leg AD is the radius. This leg AE, it's the radius. So they're both one radius long. So do we have a pair of legs that are congruent? Yes. This leg and this leg are congruent. Of course, the hypotenuse is congruent to itself, right? And that means that the triangle ADC is congruent to triangle AEC. And if the triangles are congruent, all of their corresponding parts are congruent. So the long leg of this triangle has to be congruent to the long leg of that triangle. Okay? So EC has to be congruent to DC. Okay? So that is that, and that is how we can use that hypotenuse leg theorem. All right, we're going to do one last bit, and that is working with something called the tangent segments theorem. And we've already kind of seen this, but I'm going to show you a problem about it. Okay, so here we have a circle with a center A. There's a point C that's out here. Okay, there's another point E that's down here. E and C, the line that goes between them is tangent to the circle. Okay, so they're not random points. They're points on this line of tangency. Okay, now let's see what they're telling us and what they want us to figure out. Well, they're giving us some measurements. EF, which is this point here, compared to this point of tangency. They're telling us that that segment there has a length of 12. And they're telling us that from the center out to this point E has a length of 13. And they're telling us one more thing. They're telling us that if we compare AE to AC out here, those two segments have a relationship of 1 to 3. In other words, whatever length AE is, AC is 3 times as long. So since this is 13, AC is 39. Okay, and that is all we are given. But we do know things about points of tangency and radiuses and things. Okay, so let's see what we have here. First thing we need to do, find the radius. So look. This is a point of tangency. We can connect it to the center. That would be a radius, right? We know this makes a right angle. So we have a right triangle here. And we know the leg, and we know the hypotenuse, and we're missing the leg. So can't we just say leg squared plus leg squared equals hypotenuse squared? Right? Pythagorean theorem. 12 squared is 144. 13 squared is 169. So r squared plus 144 equals 169. And if you subtract 144 on both sides, you get that r squared equals 25. And what number squared is 25? The radius is 5. Okay. That was useful. Second thing they want us to figure out is what is the length of BC. So now they want us to figure out how long is this side here. Well, you guys, from A to B, that's the radius again, right? And we know that's 5. We just figured it out. So we do the Pythagorean theorem again. Leg squared, hypotenuse squared. So 5 squared plus, we don't know what that is. We'll call that one y. I don't know. equals hypotenuse squared. So 25 plus y squared equals 39 squared is 1521. We're getting some big numbers here. Which means if you subtract 25, it means y squared equals 1496. And then you square root it, and it's 38.7, which is not a very convenient number, but that's the number. So it's 38.7 out there. Okay, and then the last thing they want us to figure out is, well then, what is the distance from E? Hang on, change colors one more time. What is the distance from this point E all the way out to point C? What is the whole length of that? And you may recall we figured out when you have a point and it goes to a tangent, those two lengths are going to be the same length. So if that length was 12, this length is 12, right? Then we have the same thing on this other one from point C. If this length is 38.7, this length is 38.7. So what do you think? If we want to know what the whole length is, all we have to do is add those together. 12 plus 38.7 equals 50.7, and we are done. All right? So those are some interesting things we can do with tangents and triangle theorems and circles. All right, so that is it for lessons 1 and 2, and now you can continue with the rest of your lesson. Bye, everybody.